No. Okay, great. Good afternoon, everyone. My name is Amir Shabar. I'm the chair of the Toronto Center of CMOS. And today we are honored to have Professor Duane Froese of the University of Alberta. Professor Froese is Canada chair, or was the Canada chair, research chair in the Northern Environmental Change. His focus is on development and understanding of the past records of environmental change in the North. It developed a framework for the Arctic climate, particularly interested in permafrost and how it is responding to climate change. He's interested in knowing how the permafrost is affecting the northern infrastructure, ecological impact it is having, and increasing contribution of the greenhouse gases, particularly methane and carbon dioxide. So the topic of today is the permafrost, a grand challenge for Canada in the 21st century. I would ask that you post your question on the chat, and at the end of the talk, I will go through the question and comments, and Professor Froese will answer those. So over to you, Professor Froese.
Great, thank you, and thanks for the opportunity to give this presentation today. So when I was first asked and sort of thinking about this, I was sort of thinking about how to kind of frame the permafrost question. And really what I wanted to do today was kind of provide a bit of an overview of really three different themes that I think underscore the challenge of permafrost for Canada as we move forward into the 21st century. And so these are the sort of ecological impacts of permafrost thaw. So this is sort of what's happening at landscapes. This is secondly, the impacts on communities and infrastructure and the sort of built environment of the North that we have to deal with. And then thirdly, and probably most of interest to this community, is probably the permafrost carbon feedback. And what does that mean for, our climate system and such? And I only really work on a couple pieces of that. I'm not really a permafrost carbon guy. Mostly my work has been on looking at environmental change and understanding permafrost and how it's changing and how it fits within the northern ecosystems. And over the last few years, my group has really moved into the applied aspects of permafrost because the scale of the problems has just been increasing and increasing. And there's just such a need to kind of try to deal with the impacts of permafrost thaw. And so today I'll sort of give an overview of that and pose this as sort of the basic idea here of a grand challenge. First of all, I just want to provide a land acknowledgement. I'm joining you here from Edmonton at the University of Alberta, and we're on Treaty 6 territory, traditional lands of First Nations Métis people. And I really want to acknowledge that really all of permafrost in Canada sits within traditional territories of First Nations and Inuit people and Dene, where we work a lot in the Dene communities of the Mackenzie Valley, which include both Dene and Métis communities. And with our work in the past in northern Yukon, central Yukon, within the Vuntut Gwich'in and Trandik Gwich'in traditional territory. So I'll be showing some slides and examples from all of these areas that we've worked in over the years. And I think it's actually really important to provide a land acknowledgement and to really highlight that however we choose and make decisions collectively to move forward, First Nations groups are going to need to be intimately involved. They're really the most affected by so much of this, and increasingly developing capacity to sort of become full partners in moving these things forward. So first of all, I want to just kind of introduce the idea of grand challenges, these sort of ambitious goals that try to harness science, technology, and innovation to solve important national or global problems. And I'll say right at the beginning, I don't think we've even articulated what that problem is in the case of permafrost. I think we've identified several different problems for permafrost that we need to deal with. Some of them may be tractable, or at least tractable at the local scale. Some of them are really so large that they're really beyond probably our scope to sort of tackle directly. And so this is where issues of emissions reductions and permafrost carbon and things come in that these don't necessarily have immediate solutions. And I think that's an area that we can kind of discuss at the end. So the grand challenge for permafrost, and really all I'm going to try to do today, is sort of define these three different problems that really underscore permafrost. So when we look at a landscape like I'm showing here from the Peel Plateau, west of Inuvik, west of the Mackenzie River, kind of towards the Richardson Mountains, we can see a landscape of ice-rich permafrost. And so if you look there and you look here in the landscape, you can see big amounts of ice here, the sort of high sort of reflective material here. This is actually ice from the Ice Age. This is actually buried ice from the Laurentide ice sheet that has been sitting there stable for upwards of 14,000 years. And we've now moved to a point where this landscape was largely stable for much of at least the Holocene, the last 10,000 years, if not 12,000 years. And increasingly, we're seeing thaw taking place in these landscapes that have appeared to be stable otherwise. And so if we want to think about sort of moving into new areas of, you know, the boundary conditions of our climate system and landscapes, this is really what we're talking about in these areas that have been equilibrium landscapes that are in equilibrium with the climate, but increasingly moving towards disequilibrium. And I think when we talk about permafrost and we think about what's happening on permafrost landscapes, it's really important to have that in your mind. And secondly, when we talk about this part of the cryosphere, it's really different than other parts of the cryosphere. So if we think of sea ice or lake ice or glaciers, where the atmosphere is essentially coupled or in contact with those pieces of the cryosphere, when we deal with permafrost, we're dealing with landscapes whereby we have vegetation and soils that essentially buffer the landscape from the atmosphere. And so in many ways, we've seen a delayed response from permafrost regions to climate warming in comparison to what's been happening over the last, say, 2 decades with sea ice, or what's been happening over the last 30 to 40 years with glaciers. So this is really where the ecosystem impacts are really accelerating. So the impacts of that thaw are accelerating. The piece that probably is of most interest to Northern people and communities is the infrastructure side of things. And so as much as the global sort of science community is very interested in the permafrost carbon problem, that's a problem that does not really hit the radars of most Northern communities or people. It's really the here and now and the accelerating here and now of permafrost thaw and the impacts and future planning and the things that need to take place that are really, I would say, at the forefront for Northern communities and infrastructure. I'm going to talk a little bit about that because I think this is the piece that probably we can get the most engagement from our government and institutions from. But it represents yet another of these sort of grand challenges that take place. And the third one that's really captured the scientific community and the permafrost community is the permafrost carbon feedback. The permafrost carbon feedback is a really difficult problem in that permafrost carbon, as I'll get into, is so diffuse and the permafrost regions are so large. We're talking about an area that's upwards of 20 million square kilometers in the Northern Hemisphere, upwards of 20 to 25% of the Northern Hemisphere land area. And so it's such a diffuse problem that it's very difficult to tackle. And we'll sort of talk a little bit about some of the issues around that. Okay, so when I talk about permafrost, permafrost is a thermal condition. So permafrost represents ground that has been below 0 degrees Celsius for at least 2 years. It's survived at least one summer. And so we have a couple of years of consecutive ground being below 0 degrees Celsius. For the most part, most of Northern Canada, permafrost started to aggrade or build into the ground following deglaciation. And so when we talk about permafrost, we're really talking about conditions of the past and conditions that formed in the past following deglaciation, in which landscapes and those diverse landscapes that existed following deglaciation began to essentially cool, freeze, and ground ice, which is really what underscores the permafrost regions, started to develop. This is a typical kind of area here. This is an area in central Yukon around the Mayo area, where we can see ice here at the surface, this is actually part of what we call an ice wedge, so part of a polygonal ground ice network that formed from cooling in the winters where thermal contraction happens because of really rapid cooling that takes place. Water accumulates within those thermal contraction cracks over hundreds or thousands of years to build these wedges of ice. And then above that here, we can see where the active layer is, the seasonally thawed zone that thaws each year. And so what's going on here in these areas, so this is an area that's actively thawing. This is an area where essentially this ground ice has become exposed to the atmosphere and started to thaw, or in the case of the ice, melt. Permafrost people kind of get really into this whole difference between thaw and melt. Ice melts, and generally speaking, we say that permafrost thaws because permafrost is not just ice. Permafrost represents gradations of sediment-rich ice or ice-rich sediment and materials. And so we talk about it thawing because it's really not just undergoing a phase transition, but it's undergoing these complex changes that take place. And so just like a turkey, we don't melt a turkey, we thaw a turkey. When we think of permafrost, we're thinking about a thawing landscape. Okay, so here's the typical kind of thing that we would see within permafrost regions where we have an active layer, or the seasonally thawed zone that thaws each year, reaches its maximum in late August to sort of mid-September each year. As the warming takes place, it usually has a relatively sharp contact with the underlying permafrost. So here is a wedge of ice. This represents a whole series of veins of ice, hundreds to thousands of veins of ice that have formed over many thousands of years. And then we can see within the active layer, there's lots of organic material in that active layer. And so when we think about what's going on in these landscapes is they freeze back around this time of the year, and the microbes that are living within it throughout the growing season or the warm season are essentially eating that organic material. And because we have relatively cold temperatures, we have very low rates of decomposition of that organic material. And for the most part, throughout the Holocene, these areas have become net sinks of carbon. And today, as those microbes are sort of chewing on that material, the duration of that active layer season, so both the temperature of the active layer and the duration of it, have led to an increased season for largely microbial activity to chew up that carbon-rich material and respire that to the atmosphere. And this has really been the change. And ultimately, the big question on the permafrost carbon side is how effective are those processes, and how much offset does that increased respiration and release of carbon to the atmosphere, how much is that offset by new vegetation growth and the changes that are taking place on the landscape, and how well do those two processes largely balance each other out? And so when we look at a ground temperature profile, this is a trumpet diagram here, which shows the active layer here. So this is the summer season temperature here in red, and in purple or blue here is the winter season temperature. And then at a depth, usually somewhere between 5 and 10 meters depth, there's a point of zero amplitude. So the point at which the seasonal differences in the air temperature do not affect the ground temperature. And then as we move below that depth of zero amplitude, more or less at the geothermal gradient, we move to the base of permafrost as it crosses this 0 degrees Celsius isotherm. And so this is a typical ground temperature profile. And so when we look at the differences in temperature of permafrost regions over time, we're looking normally at temperatures at the depth of zero amplitude or below, and looking at those changes as they've happened over multiple years in order to remove those effects of the seasonal temperature change and when you've actually made those measurements. So when we look at a permafrost map like this one for Canada, we can see these different zones from these sort of purple colors here, which is the extensive continuous permafrost zone, which covers areas like the Mackenzie Delta and much of the Canadian Shield and the Arctic archipelago. And so these are areas where mean annual temperature is below about -6, -8 degrees Celsius. Ground temperatures are below about -2, upwards of -10 or -12 degrees Celsius. And then as we move into these blues and greens, we're in what we call the discontinuous permafrost zone. So in the continuous permafrost zone, we expect that most of those areas will be underlain by permafrost. Upwards of 90% of those areas will have ground below 0 degrees Celsius. But as we move into the discontinuous permafrost zone, we're dealing with areas where mean annual air temperatures are above about -4, -5 degrees Celsius, and ground temperatures are above -2 degrees Celsius, generally speaking. In many of these areas of this extensive discontinuous permafrost zone, we're dealing with ground temperatures that are above -1 degree Celsius. We're dealing with ground temperatures that are getting very, very close to that thawing temperature right near 0 degrees Celsius. One of the things that you see when you look at this is you can see the latitudinal effects of permafrost, so the latitudinal effects of those permafrost boundaries. And that really underscores the thermal definition of permafrost. But it's really important to keep in mind, and that's what the next part here I'll get into, is that how permafrost regions respond to climate is largely dependent on the geologic history. So it's dependent on the landscape history, and especially where ground ice is present. And so where there's a lot of ground ice present, those are areas that are very susceptible to thaw. So those are those areas that we will expect to see sort of landscape and terrain effects. And so we have this combination of landscape history and thermal history that come together in sort of understanding permafrost zones. And so if we look at sort of the observed changes over the last kind of 50, 60 years, we can see the Western Arctic especially has undergone a lot of change. A lot of that change is from winter warming, especially. And when we think about permafrost, winter warming becomes really important because of really two things that are happening. In the one case, there has been increased precipitation and snowfall in particular, and snow has a really strong effect on insulating the ground and insulating the ground from those winter temperatures that are really required in order to cool the ground and keep the ground cool to kind of persist through the summers. And so the winter warming has been more pronounced than the summer warming has for most of these areas of the Western Arctic. And we can see, you know, on the order of maybe upwards of 4 degrees Celsius or so change over the last 60 years or so taking place. And the exact number isn't as critical as the sort of direction of that change. And so when it's looked at a circumpolar perspective, this comes from a recent review here looking at deep permafrost across the Northern Hemisphere. You can see that for the most part, the really cold permafrost tends to be warming a little bit more than the warm permafrost. And that's mostly because of latent heat effects. And so where the ground ice in the sort of higher Arctic and colder areas is warming relatively quickly because those latent heat effects aren't happening, as we get towards 0 degrees Celsius and we get the latent heat effects happening, we've essentially started to slow those rates of change as we approach that sort of phase transition that's taking place. And so we've actually sort of slowed some of the change, and increasingly in some of these areas, we're starting to undergo that phase transition in these areas, which results in the sort of landscape sort of scale changes. If we look at it in the Canadian context here from the Mackenzie Valley, which is probably our best instrumented and monitored area of Canada for permafrost at a sort of south to north transect as a result of infrastructure projects over the last sort of 50, 60 years with the generations of the Mackenzie Valley pipeline projects and such. We can see, you know, if we look at, say, areas like Fort Simpson, which is sitting, let's see, way down here, there's Campbell Bend. So yeah, kind of down into this area here and up towards Inuvik up here. We can see that more or less since about the mid 70s or so, we've seen this overall warming trend with the ground temperatures in these areas. Oh, sorry, these are air temperatures. Sorry, I'm going to show you the ground temperatures in just a second. Yeah, here we go. Here's the ground temperatures. And so if we look at the ground temperatures, and so here's around Toledo. So Toledo is a little Dene and Métis community here in the central Mackenzie Valley, where ground temperatures are on the order of maybe minus 0.1 degrees Celsius here. As we move a little further north towards Norman Wells, so in this area here in the central part of the Mackenzie Valley, we're dealing with ground temperatures maybe on the order of minus 0.5, minus 0.6 degrees Celsius. And as we move a little bit further north, kind of towards, say, Fort Good Hope, which occurs right at this sharp bend here in the Mackenzie River here, the ramparts of the Mackenzie right in this area here. We're dealing with ground temperatures a little bit cooler, around minus 1 degrees Celsius. So important to think that across these regions, we're seeing warming taking place throughout the ground temperatures. Most of these areas are, especially through the discontinuous permafrost zone, are very close to the 0 degree Celsius isotherm. And so even in these are all essentially undisturbed sites. We're getting very close to thawing temperatures in these areas. So these are sort of deeper boreholes here between about 8 and 15 meters or so depth. Okay, so if we take a look at ecosystems and landscapes, so first of all here, when we look at the landscapes of the north, there's a strongly variable response to the landscape to warming temperatures. And so as much as the permafrost boundaries represent sort of these latitudinal changes across the landscape, how the landscape responds is really reflecting the nature of the ground ice, especially that's distributed to the ground. So here in this area of the Tuktoyaktuk Peninsula, we can see degrading ice wedge polygons. And so these ice wedge polygons that represent areas where we had thermal contraction, cracking, and development of ice wedge polygon networks. Essentially water getting trapped in these landscapes, leading to expansion as that capacity, that heat capacity is held from the water, and essentially thawing more and more permafrost, and especially ice-rich permafrost, which has potentially a positive feedback effect. In the areas west of the Mackenzie Delta here, in the Peel Plateau, where there's a lot of buried Laurentide glacier ice towards the margin of where the Laurentide ice sheet was, these very large thaw slumps that have developed that are bringing large amounts of debris on the order of 10, 20, 30 meters of headwall retreat in a year, and bringing that material that has accumulated through the Holocene down into these rivers and essentially overloading some of these streams and watersheds, overloading them both with carbon-rich material from permafrost and potentially metals and things like this that have accumulated naturally in these landscapes and are now sort of being distributed in these areas. In the central Mackenzie Valley, so if we're in the area around Norman Wells and these areas where we have extensive peatlands that have accumulated, we have these areas of thawing peatlands that are taking place where essentially these peat plateaus and these sort of yellow colors here, which are what we call a caribou lichen or cladonia covered surface, have permafrost underneath them, and then these fens and bogs that have developed that essentially no longer have permafrost. So in this area here, we're looking at an area that has permafrost on the order of maybe 15-ish meters depth, 20 meters depth. And we've now developed talus across these with these fens that are cross-cutting these landscapes. And then as we move even further to the south around Yellowknife, we can see these thaw lakes that have developed within some of these old glacial-lacustrine basins. And so we have little areas where permafrost is preserved on some of these pulses and peat plateaus, but otherwise we're seeing the expansion of these lakes that are taking place in these areas as warming keeps happening. The Northwest Territories Geological Survey, my colleague there, Steve Coquel, has done a really nice job of essentially mapping permafrost change at sort of a subcontinental scale. And Steve did a really nice job of this with a group of our students and some other folks that have been involved in this, and essentially trying to look at systematically the types of changes that are taking place across the permafrost regions of the Northwest Territories, right from, say, Banks Island, Victoria Island, all the way south towards the Alberta border, for example. And so if just looking at thaw slumps, which are these areas of abrupt thaw, and I'll tell you a little bit more about these in a second, you can see that they're mostly found in the areas around where the sort of the limit of the Laurentide ice sheet was, so the boundaries of the Laurentide ice sheet, because most of these are associated with essentially relict buried glacier ice that was stable for most of the Holocene And as we move back onto the, say, the Canadian Shield, where we don't have an awful lot of excess ice, for example, so a lot of ice that exceeds the pore space of the host sediments, we see relatively little in terms of thaw slumps in these areas. Some differences here, I'll show you some from this area here in the central Mackenzie Valley that we've worked on. But these are sort of areas where essentially the geologic context or geologic history predisposes parts of the landscape to thaw. So examples here of buried glacier ice here up towards the Mackenzie Delta. Throughout a lot of the central Mackenzie Valley, we had a very large glacial lake McConnell, and another one here, Glacial Lake Mackenzie, that existed along these corridors here. And so that resulted in a tremendous amount of fine-grained sediments that accumulated, much like most of the proglacial lakes that we had in Canada. And so after these lakes drained, they were exposed to the atmosphere, and permafrost aggraded within these. And so as the cooling front, as the air temperatures are sort of transferred into the ground, it actually sucks the water up towards that cooling front. And so there's a depth of around 4 or 5 meters or so depth, which tends to be where these big, thick lenses of ice essentially accumulate. In most of these cases, these landscapes have been thaw stable, for the most part, or at least been stable for most of the Holocene. But increasingly now, as we've mapped landslides and looked at these, we can see that these landscapes are really in transition as warming has taken place. And just some of these ice-rich landscapes here. And if I just go back here, just to kind of give you a sense of scale, there's a helicopter down here sort of showing, this is a very large landslide called the Johnson River landslide that happened in 2016, for example. Okay. And so we end up with, when we look at what's happening with permafrost regions, much of these areas are affected by essentially what we'd call gradual thaw. So this is where our active layer is increasing as a result of increased air temperatures and longer warm seasons that are taking place. And so there's a couple of things taking place. Many of these areas, as they thaw the ice within the ice-rich permafrost at the base, that ice-rich permafrost in the base or towards the top of permafrost has what we call excess ice. And I'll talk about excess ice here in just a minute. But all excess ice means is these are areas where the ice exceeds the pore space. And so when the ice exceeds the pore space, when we have thaw taking place, we get subsidence of that landscape taking place, and we release that water into now the active layer, where it can potentially be affected by, accumulations in ponds, which can hold heat, which can essentially drive greater thawing of that landscape. But it also, where we have gradual thaw, we're increasing the duration of the thaw season, and we're increasing the active layer temperatures. And so this essentially enhances microbial activity. And so when we think about the permafrost carbon feedback, we're really talking about that increase in that microbial activity through the season and into the fall. And one of the big revelations that's really happened in the last sort of 5 years or so is getting a better handle on the duration of that CO2 exchange that takes place and the importance of the winter respiration from the active layer into the atmosphere. And so this is kind of what we see in the landscapes. We mostly see a wetting of the landscapes where ice-rich permafrost has thawed, particularly in these areas where we have low relief landscapes, glacial-lacustrine basins and such, where this ice-rich material thaws. So this is just an example here showing you sort of some of these veins of ice. And so even in this kind of core here, we might be looking at 50 or 60% of that core is essentially pore ice. And so as it thaws, it essentially kind of turns into a soup. And important, the way I kind of keep it in mind is that at -5 degrees Celsius, permafrost more or less has the properties of concrete. And at 0 degrees Celsius, it more or less has the properties of sort of porage. And so this is really the landscape transition that can be taking place. And so that subsidence on the landscape. So here's an example here in one of these peat plateaus. You can see ponding of the water surface here. These are this yellow lichens, we call them caribou lichens or cladonia type lichens. They only exist in areas that are elevated above the water table. And so we can see where they're starting to be to subside and now being flooded and essentially transitioning from these dry kind of mosses to sphagnums and sort of wet condition sort of mosses. And so this results in a transition of microbial communities. This results in a transition for sort of the dynamics that are taking place at this local scale. And this is one of the great challenges with permafrost is there's a lot of variability or heterogeneity of landscape processes that are taking place across these regions. Okay. Now, the other type of thaw that's taking place is what we consider abrupt thaw, or what we call thermokarst. And so when we look at sort of particularly where we have any kind of slopes taking place, where we have our active layer and we have our ice-rich permafrost, if we disturb that active layer and expose that ice-rich permafrost, we can essentially drive it towards a landscape that's unstable. And quickly we get headwall retreat and what we call thaw slumps and these things. And these tend to occur relatively quickly. And one of the big observations over the last 15 years has been the rapid increase in both the frequency and magnitude of these thaw slumps across northern landscapes. Examples here from the Keel River. So these are sort of some of the most dramatic landscapes that we see associated with permafrost thaw, and sort of exposing of this ice-rich permafrost. And once that happens, it just essentially keeps retrogressing, or that head wall keeps retreating back while that ice-rich permafrost is exposed, and translating or moving that material down into the lower areas until usually that vegetation cover, it either runs out of ice-rich permafrost, or that vegetation cover essentially slumps over and starts to insulate that ground ice from future thaw. Typically, these things will last for 10 or 15 years or so, and then they sort of heal over and sort of stabilize. So examples here of these, and this is really where we're talking about landscape change. So this is an example here within the central Mackenzie Valley, where we can see these head walls essentially are retreating rapidly, overloading the streams, resulting in ponding that's taking place at a local scale. This sort of switches us to anaerobic conditions, and these are the places that you would expect to have greater methane contributions from these areas, as opposed to the aerobic sort of respiration, where we'd expect microbes to be mostly releasing CO2 to the atmosphere. Just to give you an idea of one of these really impacted thaw landscapes here, kind of just a helicopter view through one of these landscapes, looking at the impacts of these thaw slumps and moving essentially ice-rich material down into the valley bottoms here at in an area of the Sawtooth region of the central Mackenzie Valley foothills. Now, it's important to note that this isn't happening everywhere the same. Certain areas of the landscape are more sensitive, and these are the areas where we're seeing these sorts of changes taking place. And that either represents greater sensitivity because there's more ice-rich material in the ground, or perhaps there have been events like forest fires or something that have preconditioned that landscape to be more sensitive. In this area here, we had a whole series of forest fires in the mid to late 90s through this area. That's this check pattern here, which essentially shows the big forest fires from the mid to late 1990s. And so in 2005, there were about 100 or so thaw slumps within that area that were essentially distributed only really within the areas that had been burned in the 1990s. One of the effects of forest fire is to essentially remove part of that vegetation cover, and so then removing that insulation of the permafrost from the atmosphere. And so in this case here, this comes from one of our PhD students, Joe Young, who just published a paper on this stuff in GRL. And looking at these changes over the last sort of 20 years or so, showing that going from 2005, where there were about 100 that had developed in these areas affected by the forest fires, to more than 400 by 2018. And most of the area around it has almost no thaw slumps in it, the areas that were not burned. And that isn't to mean that those areas are not going to be affected by thaw slumps. It's just that the areas that have already burned are showing us where the most sensitive landscapes are. So they're showing us the distribution of ground ice, but because the thermal regime has been altered in these areas, these are the areas that are failing now. But as climate change keeps kind of moving forward through these regions, we would expect to see these entire landscapes to be affected similarly to what we're seeing the areas of the forest fires, for example. So this is a recurring story across the north of sort of pieces of the landscape that are most sensitive, that are being impacted by these events today. Some examples of these are some of the deep permafrost failures that have taken place. We've looked at a bunch of these through the area that have all taken place in the last 5-6 years. So again, telling us about big changes in permafrost areas, and probably these are really precursors to even more widespread failures that are happen going into the future. So when we talk about thermokarst, I think it's really important to keep it in your mind that we're not talking about everywhere being affected. We're talking about areas where there's a lot of ground ice that are thaw sensitive, and areas where we would expect those increases in air temperatures to have more immediate impacts. So these areas that are affected by fire, especially. Fire is probably one of the biggest variables that we don't have a great handle on, and it's probably going to drive a lot of the changes that take place in northern areas as we move into the future. As forest fires have increased, both the size and magnitude of these have increased over the last few decades. Okay, so looking at some of the second issue here, communities and infrastructure. So excess ice, and this is a video from Brendan O'Neill, who put together this little video here, showing the impacts of excess ice. So these are 3 different permafrost cores with varying ground ice contents. So on the far left here, a really ice-rich permafrost core where about 70 or 80% of it is ground ice. In the middle, a relatively moderate ground ice-rich core. And on the right side here, a relatively ice-poor core. And you can see with each of these varying sort of impacts of that thaw, where essentially there's nothing left on the far left, and the one on the far right, there's just a little bit of water in the bottom of it. And this is really illustrating the role of excess ice. And so it's illustrating that in the areas where there's a lot of ground ice within the sediments, these are the areas where we expect a lot of impact. And so when we're dealing with communities and dealing with infrastructure, a lot of our job is to map the ground ice distribution and try to predict the ground ice distribution in order largely to avoid it if possible. Oh, what am I doing here? There we go. And so the impacts of this is Dawson City. This is probably one of the most photographed buildings in Dawson. It was the old blacksmith shop. So Dawson City was built on an area essentially where we had a floodplain, and we had maybe a meter or so of ground ice within those organic rich materials. And after that stuff was built on top of it, essentially we saw thawing and subsidence of some of these buildings, but it was more or less limited to the amount of ground ice that was present within those areas. Today, in northern Canada, we have somewhere around 3,000 or 4,000 kilometers of roads. And so the impacts of thaw, so here this is a photo from my colleague Guy Doré from Laval University along the Alaska Highway, and sort of showing the subsidence along the edge of the road. And a lot of this is happening because snow accumulates along the shoulders of these roads, which essentially warms the area along the margins and essentially results in where there is ice-rich permafrost subsidence taking place. And so the settling of those roads taking place. So this is this part of the Alaska Highway is an area where the maintenance runs several $1 million a year just to keep up with this part of it. Other areas here on the Dempster Highway where we have ground ice, again, subsidence and thaw taking place. There are some areas likely of the Dempster Highway and the northern part of the Dempster Highway where the road will likely need to be rerouted over the next decade or so because of ground ice and trying to avoid that ground ice. And so this is where some of the costs are really coming up for these areas. It's very difficult to come up with a really great number on the cost for roads in northern Canada, because with roads built in permafrost, we expect much higher maintenance costs at the beginning, but where the roads ultimately need to be rerouted, those costs can kind of move up tenfold. The Inuvik-Tuktoyaktuk Highway here, north of Inuvik, built largely in an area, especially the southern part where there's a lot of ice-rich permafrost, opened in November of 2017. I think annual maintenance, the numbers I've heard, are about $30 million a year to maintain this road. So these are really expensive roads to maintain and try to avoid that permafrost and ground ice loss. Much of that area, this is kind of just that area of the Inuvik-Tuk Highway, looking at some of the ground ice that's exposed in these thaw slumps that the road kind of passes over top of. And so the job is both to keep the road bed elevated, try to avoid accumulations of snow along the margins, and all of these sort of strategies to try to keep that road and the ground below it as cool as possible, and especially allowing winter cooling to take place. Okay. This is one of these maintenance sheds along the Dempster Highway, and these are sort of some of the costs and the infrastructure things you see of thaw settlement taking place within this building here. Doesn't look too bad from the outside, but then once you get into the inside, the accumulation of water and the heat that comes with it, essentially driving more ground ice loss from these areas. Okay. We've been working now for the last 5 or 6 years with communities in the Mackenzie Valley and looking at community permafrost mapping. And most of this is really about ground ice mapping within these areas. This is the community of Toledo, which is at the junction of the Great Bear River and the Mackenzie River in the Central Valley, about 100 kilometers or so south of Norman Wells. And through this area here, we've been working on essentially drilling permafrost within the community and really trying to stay ahead of the community in terms of laying out those areas that are best avoided for where we have a lot of excess ice, or permafrost that has a lot of excess ice that's going to be impacting future development. A lot of these northern communities are growing rapidly. So the community of Toledo has built 2 new subdivisions, for example, over the last decade to try to come up with new housing developments to support sort of a growing young population. And one of the challenges is where we have this ice-rich permafrost is to essentially outline where that is present and try to avoid future development in those areas. And so these are assessments that we've been doing with these northern communities, but there's just a huge need to do a lot more of this kind of work. If mistakes are made in these areas, it can run easily into the millions of dollars if you have to start relocating infrastructures or housing developments and these things within these areas. And so this is a big effort of our group, is to really work with some of these northern communities and the Northwest Territories government to kind of outline some of these issues. Right now, the Northwest Territories Association of Communities estimates right now that the permafrost thaw costs for communities, there's 33 communities in the Northwest Territories, is probably about $50 million a year at present. And for the most part, we're still early on in seeing the effects of climate change on these northern communities. And I would expect that number to go up a lot as we kind of move forward with climate change. Exactly what that number is some folks have tried to come up with it, but it's a difficult one to come up with. But I would suspect Canada for sure will be running into the billions of dollars of cost for northern infrastructures and communities in the not too distant future. Okay, the permafrost carbon feedback, just for the last few minutes here. So initially I was talking about, the cold temperatures result in relatively low rates of decomposition of carbon and organic material. And this has resulted in essentially a net accumulation of carbon as a sink over the Holocene over the last 10,000 years. And so that number is somewhere around, say, 1,600 gigatons of carbon for permafrost regions. About half of that sits in the upper 2 to 3 meters. And the best estimates now are that if it isn't already a net source of carbon to the atmosphere, it's likely to be soon. And so even if we're talking about losing, so this number here is almost double the amount of carbon in the Earth's atmosphere, and certainly not all of it will be mineralized and respirated into the atmosphere. But even if we're talking about a few percent of that going into the atmosphere, it becomes a big number and a piece of sort of the global climate problem here that's really not well considered within even the Earth system models that exist today. And certainly no countries are considering the permafrost carbon feedback within their net zero sort of targets as they move forward. Certainly Canada is not. In 2019, Sue Natali from Woods Hole came up with this paper, which was really trying to come up with the better estimates of net respiration throughout the year, which included a whole series of winter measurements and sort of summarizing those and looking at different RCPs, the 4.5, 8.5. And basically at the 4.5 RCP at the time, they were suggesting that there was probably a net loss of carbon from the permafrost regions of about 1,600 teragrams of carbon, or about 1.6 gigatons, relative to about 1,000 teragrams of new growth taking place. And so overall, there was maybe a 600 teragram net contribution to the atmosphere that was likely taking place from the permafrost regions. If we scale that to Canada, that gets somewhere close to Canada's national emissions. People have kind of pulled back a little bit on that numbers because the uncertainties are as high as they are. But I think the directional change, I think, is an important one that they really documented, and this has been consistent in the most recent reviews, is essentially an increase in those net contributions as we move forward, even under moderate RCP of, say, 4.5. In last year, permafrost carbon emissions, again, was looking at similar things. And in particular, when we look at Canada, we can see that in Canada, the most important permafrost carbon regions are the area of the Hudson Bay lowlands in sort of northern Ontario and Manitoba, and the area of the Mackenzie Valley out to the Mackenzie Delta here, which are areas essentially of extensive fine-grained sediments with really high rates of organic accumulation. And so these are probably, if we wanted to think of priority areas as Canada moves forward, these are some of the most important areas probably from the permafrost carbon side of things. The big themes that have come from this work are that, the abrupt thaw, those types of thaw slumps and those changes that we're seeing that are largely driven by those ice-rich landscapes are still not considered within these. And most of these models are really only considering this sort of gradual thaw that's taking place. And so the other disruptors, things like fire that are taking place across these northern regions, are likely to become really important contributors to how these landscapes change and what the net emissions are as we move forward. So a project here, just as I end off, that I would highlight here is Woodwell, the former Woods Hole group, led by John Holdren and Sue Natali there, have developed this new Permafrost Pathways project that is about 6 months old now. They're working across the Circumarctic. They were planning to have a pretty big presence within Russia, but I think they've pulled back from that and now looking at putting more of that infrastructure into northern Canada. But it's really to increase on several themes from the communities and infrastructure, but especially the permafrost carbon feedback piece of this, to increase the distribution of flux towers across northern Canada, across Alaska, and to some extent support the existing flux network that exists within Siberia and Scandinavia, and to really try to improve those uncertainties and those estimates of permafrost carbon. And a big part of that is really around trying to get a better handle on the winter emissions piece of it to try to get at those overall contributions. So just to kind of wrap up here, in terms of a grand challenge, I think there's some really big problems here that Canada has to kind of come to terms with, and I don't think we're doing it very well at present. Upwards of 50% of Canada is underlain by permafrost. We're really one of the big permafrost nations. That scales up towards of maybe 20 or 25% of the Northern Hemisphere. And the problem is really diffuse. The distribution of permafrost carbon and permafrost is such a large landscape scale problem that there are no real immediate solutions. The best, overall solutions are sort of, emissions reduction sort of strategies, but so far we're not making a lot of progress on that side. The best estimates right now are that we're either very close to the permafrost regions being net emitters of carbon to the atmosphere. And if we're not already, we are likely to be soon. But those estimates are really still plagued by really large uncertainties. Across all levels of government, though, I think this is a big one here for Canada, is the problems of adaptation and preparation and sort of understanding what's going to happen on the Canadian landscape. And we're really not doing this very well. And I think at present, we have no overriding permafrost national strategy. And this is something that I hope we'll see Canadians start to take a lead on. There's several major lobbying efforts. The Cascade Institute now, the group that I've been involved with now led by Thomas Homer Dixon, is really trying to bring the permafrost issue in Canada at a higher sort of political and policy level. But this is really a recent addition. And I think right now we're really not doing a very good job of it. So I'm just going to end off there because I think my time's about up and kind of leave it open for some questions. Thanks.
Okay. I don't see any question on the chat, but people can go ahead and either post it on chat or ask directly. Okay, I don't see any. Could you also comment on the methane which is stored in these permafrost, and what is the implication of that in terms of the study that you have done?
So for the most part, methane is a relatively small contributor of greenhouse gases to the atmosphere from permafrost regions. It mostly happens in areas where we have waterlogged soils or water on the landscape that results in mostly archaea that are sort of methanogens to the atmosphere. But about 90+ % of the estimated greenhouse gas emissions from permafrost regions are from CO2. And so as much as methane is one that gets a lot of attention, the bigger challenge is probably going to be in CO2 and CO2 management as we move forward.
Mm-hmm. Okay. Any other questions? I don't see any. Well, if there are no other questions, then I'd just like to thank you very much for this very enlightening and a topic which is really not discussed that much, in terms of what is happening in the north.
Great. Okay. Well, thank you.
Thanks very much.
Okay. Bye-bye.
Bye.